The brain can make new cells, and this is how we found out about it. Oh, no, one more slide first. What's new about being old is that there is more variability among us than we ever appreciated before. In other words, people don't age at the same rate, in the same ways, or with the same kinds of decline. That's one thing we know. A second thing we know is that aging is modifiable. It used to be, you know, that old joke of, you know, what's the secret to successful aging? Choose your parents wisely, okay? Because we thought it was all in the genes. And even though I know it's not in the genes, well, actually about 20% is in the genes, I'm still glad that my mom's old. I think it gives me better luck. But the truth of the matter is, as a scientist, I know better. We can actually modify the way we age. We can change and modify our risk factors for different diseases. And then finally, I don't know why my thing is stuck. There we go. Maybe. Oops. A little slow on the uptake. We'll just see what happens there. Because the last bullet point has the word neuronal plasticity. How many of you know that word, neuroplasticity? Some of you know that word? Neuroplasticity is, I think, the great discovery of the it's not coming, is it? Is the great discovery of the 1990s, the decade of the brain. Neuroplasticity, I love technology, but it has gotten ahead of me today. That story is not ready to be told yet. Let's try it back one more time before you hear that bird. We'll see what happens. Neuronal plasticity refers to the fact that the brain, in fact, makes new cells and has mechanisms for self-repair, which have to do with making new branches, making new connections when cells die off. So the idea that we've always believed that the brain can't repair turns out not to be true. What we don't know is how to make that happen in all parts of the brain. We don't know yet how to make that happen in areas affected by stroke or Parkinson's disease. But we are learning, because the story that I'm trying to get to, the story that I'm going to tell you about these songbirds 20 years ago, put us on a path of discovery that is nothing short of just fantastic, exciting, phenomenal, and holding out so much hope for brain diseases of the future. So, don't know what's happening here, but let's see. Genesis, neurostyle. Anybody know what that sweet sound bird is? It's not a canary, but it ought to be, because that's the title, right? No, not a sparrow. Very good. Did you look in your handouts, or we have some bird lovers here? Bird lovers. Bird lovers looking in the handout to confirm. Okay, good. Well, that is the black-capped chickadee. And here's how the black-capped chickadee got us started on this path of learning that we make new brain cells. For those of you who, like me, like words and who want to stimulate their own neurogenesis this morning, let me break the word down for you. Genesis, you recognize, first book of the Bible, means in the beginning, right? It means to create. That's its root word. So the word neurogenesis means making new brain cells. And here's the beginning of the story. Neurogenesis, creating brain cells or neurons. This is the guy that I like to give the credit to for getting us back on the right track. Dr. Nottenbaum at Rockefeller University in the 1980s began his study of birds because he was very interested in looking at songbirds as a kind of animal model for new learning. Because bird fanciers know, I didn't know this, but bird fanciers know that actually birds learn to sing. That's not innate. That in fact, you can study bird song, apparently, and look at very young birds aping, miming their adult bird teachers in erratic ways when they're quite young. And it takes them a while to crystallize that intelligence to crystallize the ability to sing that song. And so he found in this a good model for looking at how humans learn as well, because a lot of our learning, if you think about it, is oral and imitative. We listen and we learn. So he was very intrigued by this. And as he was doing his research, he saw two other very important things. One is that when birds are learning to sing their mating songs in the spring, a part of their brain called the hippocampus gets bigger. It increases in size, and it shrinks when they're not mating in the fall. The other part of the hippocampus, because it's got some different regions, increases in the fall, because that's when you have to remember where you've hid your food. And it turns out that songbirds with bigger hippocampi, the plural of hippocampus, for those of you who had Latin, or for those of you who didn't, the hippocampi of birds is bigger in those birds that can remember longer where they put their food. Pretty cool. So Fernando Nottenbaum published a great paper, and by the way, I forgot to include it, but I'm going to post it on my website. He wrote this great paper that was published in Nature magazine telling this story. There were, of course, many skeptics. The skeptics pointed out that, well, that's sweet for birds, but what's it have to do with the rest of us? Because after all, humans are really only interested in themselves. Well, I mean, not that we don't care about other species, but we are kind of species-centric. And they pointed out that no one had been able to demonstrate neurogenesis in primates. Moreover, the skeptics said, what kind of a way would that be to make a brain that was constantly making new nerve cells? What would happen? It would be like, they said, constantly replacing the hard drive in your computer. Like, what sense would that make, as opposed to putting in some new software applications, like, sort of every so many years? That in fact, humans were going to have to content themselves that from an evolutionary standpoint, we had lost the ability to make new brain cells. And the mechanistic view of the brain as being sort of like a computer lent some kind of sense to that. People say, well, that kind of makes sense. Maybe we don't make new brain cells if it is kind of like a computer. Others were not daunted. And particularly Dr. Elizabeth Gould and Bruce McEwen said, we don't think this is going to just turn out to be confined to songbirds. We, in fact, think that those who have not been able to show neurogenesis in primates haven't been going about it in the right way, haven't been using the right techniques, or haven't been looking in the right locations. And in particular, they noted that when people go to humans, when they go to primates, they like to look at the newest part of the brain, the neocortex, because those are our centers of higher learning. So they said, let's go look in the hippocampus, where Dr. Nottenbaum found it for the songbirds. So they went, looked in the hippocampus, and found primate neurogenesis. It took a guy by the name of Fred Gage to bring this story forward to humans in the late 1990s. Dr. Gage was trying to find a way to get hold of human brain tissue well, let me start over.